All right, so I just briefly wanted to go over some updates for the amplifier and go over some mods that were recently made for the power section of the amplifier, because there's some helpful information that'll aid in the construction of a power supply for those that are building an amp with a full wave rectifier that's not utilizing the center tap for the standby switch. So if you recall, this was the power supply layout for the amplifier. Here we just have a voltage source. Again, this is LT Spice, and here we have a voltage source instead of the transformer. But this could be, you could look at this as a secondary of the transformer that's going into this resistor, straight into a capacitor, into another low pass filter, another one. So 3 low pass filters on this circuit. Now this works fine, and this still stands. But the issue here is that I want a standby switch on this amplifier, right? Because I don't want B plus to be at the tubes before they warm up, right? That's why you have a standby switch on your tube amps. But in this case, I wanted to use a really small amplifier, or a small power transformer, excuse me, and because of that, I'm having to use the whole winding of the transformer and having to use a bridge rectifier as well to get the voltage I want. So if I was using a full wave rectifier, I'd only get half the voltage that's displayed here. But I need that 420. So to do that, I need to use a bridge rectifier. Now the only problem with that is using a bridge rectifier causes me to have to leave the center tap open, so I don't use the center tap. So using the center tap on a transformer, on a power transformer, is actually very safe and very useful when you're designing an amplifier. And that's why it's very common that in a tube amplifier, the center tap will be utilized as a way to turn on your B+. The way this works is your rectifier will be a full wave rectifier, so it's using 2 diodes to rectify your secondary voltage. And the center tap will have a switch on it, which we know as a standby switch, and that switch will go from the center tap to ground. So that full wave rectifier is basically floating until that switch turns and the center tap hits ground. Then the circuit is fully activated, and that's how you get your B+. In this case, using a bridge rectifier, as we can see here, I did another drawing of the new power supply layout. This is our bridge rectifier here. Using this bridge rectifier, now we can utilize the center tap. So to circumvent having to have a high voltage, high B+ voltage at our standby switch, what I've done here was make a circuit with a time delayed relay that will turn on the high B+ voltage when I flip the standby switch. So this relay is operated by 6 volts. The 6 volts will turn on this relay. So if we walk through this circuit, we have a 6-volt filament going into the bridge rectifier. Then it's going into a switch, then to a 2.2K resistor, then into the 470 microfarad capacitor, into an NPN resistor, which is going to be used to turn on the relay in the B plus section. This would be the filament section. And now going into a capacitor to filter the filament voltage for the 6SN7, of which I also have regulated now. So if you remember early on, I was trying to use two 6SN7s, realized I didn't need it. I wanted to make it simpler, so I simplified it and used one 6SN7 and the KT66 for the output tube. Now, because of that, I've actually left me with a little bit of more current. So it gave me the possibility of using a DC winding or DC voltage for this 6SN7, which is nice because that gives me more assurance in the noise level. So that'll bring the noise level down significantly. And it also gives me a regulated voltage supply. Because one thing that I don't think I've mentioned until this point is that a 6SN7, especially when it's being used in any kind of configuration where there's going to be a high cathode voltage, it's prone to make noise. So these 6SN7s are great tubes, but when they have a high heater cathode voltage, which in this case it will, because if we look at our schematic again, we see that the second stage of the 6SN7 is a cathode follower, which will have around 82 volts at it. It'll be 82 volts at that cathode. So having a DC heater on there will significantly bring our noise level down. So I have a regulated supply for our 6SN7, and I'm tapping the beginning of this 6-volt winding to get to the KT66. Now, I would also regulate the KT66 voltage if I had enough current, but this is only, I believe, a 2.2 amp winding. So if I had something maybe about 3.5 amps, I could then use a regulated supply for the KT66 also. But going forward, this is now our standby switch. And this transistor and this capacitor, which is going to be our time constant, is what's going to operate this relay. This would be it can be a 5 to 10 volt relay. So whenever this relay realizes 5 to 10 volts, the switch will flip and then go into this full wave rectifier, this bridge rectifier, all the way into all the low pass filters, and then into this LED, and that'll be our standby LED. So when we flip the standby switch, there'll also be an LED to indicate that the standby is on and the amplifier is in full operation. So this is great because now, instead of having 380 to 420 volts at the standby switch, now we'll only have maybe 6 to 10 volts. It'll probably be maybe 8 or 9 volts that ends up being at this switch that'll operate this transistor and going into this relay. So this is really just something that's done for safety and is really crucial. I would not want to build an amplifier that had, upwards of 300 volts at the switch. It's just impractical and unsafe. So if you ever run into this scenario, this would be the thing to do. Is to have a switch operate a transistor that would then operate your relay. Now, what's even cooler here is if you can go on to a site called Every Circuit and build this. I built a replica of that circuit here, and I can actually demonstrate the operation. Now, I didn't build in the voltage regulator circuit because they don't have an inbuilt voltage regulator in here, and that's really not necessary for what I'm trying to show here. I also didn't build out all the low pass filters in the B plus section because I'm running out of schematic space really on this grid. And again, it's not really relevant to what I'm trying to show you here. I just want to show the operation of this time delay relay operating the B plus that would then turn on the high voltage indicator. So this is our 6-volt winding, which I have here about 8 volts because that'll be what it's going to be around when it's rectified. And I have our B plus at 420 volts. And that B plus is going into this relay, which is normally open up until it hits 5 to 10 volts here at the coil, and then it'll turn on the rest of the circuit. So this is what's really cool about this Every Circuit website, is that it's able to simulate the operation of switches, which is something that you normally can't do in a lot of SPICE programs. It also has the ability to turn this LED on. So you'll see this LED glow slightly when I turn this circuit on. And you'll also see the current flow. So keep in mind that this capacitor here, the 470 microfarad, is going to be our time constant. So if you wanted this to go quicker, you would lower the microfarads, and if you wanted it to take longer, you would up the microfarads. Right now, the time constant is about 1 second. So after I flip this switch, which would be the standby switch that now has a low voltage at it, which is much safer again, and that will start to charge this capacitor, and this capacitor will take about 1 second to charge enough so that it can complete the junction in the NPN transistor and then go into this coil, the coil of this relay, and flip the switch. So now let's see how it operates. 1/1000, and there it is. Now you can see that the current's flowing through the circuit, and you can see that the LED is glowing green. Now if you shut it off, the relay goes back to being normally open. I'll do this one more time. Now our B plus is on. So again, just a really great tip, something to keep in mind when you're designing. Try to keep your high voltage out of your switch that's going to have human contact on there, or that's even going to have a contact on the chassis to ground. So if ever that switch fails, that could be very problematic. This is just the safest way to handle that. Now we don't have high voltage at this switch. The high voltage is going to the relay. So if ever that switch did fail, it would only be 5 to 8 volts at this switch and not 420. So there you go. I hope you all enjoyed. Thank you.